Morning, everybody. All right, a couple little update things. This morning, I posted this announcement. I just wanted to point this out. I went and did some sleuthing online, found a PDF from a class in somewhere in Oregon, I think, and I edited it a little bit. Okay, so what this is just a bunch of situations, right, where you can practice doing Lenz's law, right? So what we've got here is like a circular coil entering a field that's pointed out of the screen, right? And you're supposed to determine whether it goes clockwise or counterclockwise. I blanked out all, you'll see these little things here. I blanked out all the answers, right, so that you could practice. And there's just various different scenarios for what's going on. The one thing that was a little weird to me is they called, like on both of these columns here, this is what they're calling the front of the coil. It's like the part of the coil that's closest to you, right? It's supposed to be 3 dimensions. We're looking at it from the side. So what they're talking about is like, what direction does the current flow? Basically up or down on this side that's closest to you. That was a little bit weird to me. But again, there's just 3 pages, and each page has got 4 times 4, 16, right? Different practice things for you to go through, right? I also provided for you the one with the answers, okay? So it's the same document, but with the answers not blocked, right? So you can go back and check yourself. But as always, like with any of these conceptual things, you really want to give your brain the benefit of trying it before you see the answers. Like really try and see where you keep making mistakes and what you're not understanding, right? So that's just there for you. You can do it or not. Just let me know if you do use it, whether it was useful to you or not, and then I know to kind of do it. We used to have a website. There used to be a website that would pop up, like it had like 80 different situations. It would just randomize, right, which ones they show. It was a little bit like flashcards, but that website went away. I blame TikTok. All right, so there was that. What we're going to try to do today is, we're going to get rid of this first. Close window. There we go. I know I keep sort of, I don't know, beating Lenz's law kind of like a dead horse, right? But let's just watch a video. Can't do this and think it's talk at the same time. Here we go. There we go. Okay. That is going to hopefully visually help you understand a little bit more about what's going on with Lenz's law in general. This isn't specifically about right-hand rules or any steps like that, but it's this concept and idea of what Lenz's law is able to pull off. Here in this animation, they're going to have a coil of wire, right? And that up arrow that you see there is the magnetic field that's being created by the wire. And then there's these blue vertical lines. That's the magnetic field that's external to that circle, that loop of wire. Okay? And they're going to change the density of the blue lines to change the strength of the magnetic field. Mr. Balogh, check the audio. Haha. Remembered to do it first time.
Current flows through a coil of wire whenever the magnetic flux through it is changing.
Right, so that field is decreasing, right?
The current flows one way if the flux decreases, and the other way when the flux increases. But the current induced in the wire also creates a flux of its own, whose direction depends on the direction of the current. The flux created by the induced current always opposes the change in the external flux.
So it's pointed up, and then as soon as it changes, it starts pointing down.
It is known as Lenz's law. The net result of both fields added together is to slow down the rate at which the magnetic flux through any circuit is able to change.
So this last picture right here is when you put both fields together into a net field, right? And so what Lenz's law tells us or shows us is that any circuit, any coil, wants to slow down the rate of change of magnetic field through it. And we saw that with the magnetic brakes that I was demonstrating last time, and that big long tube that I had, dropping the magnets through. Anytime you have a changing magnetic flux, a coil or a circuit is going to want to slow down the rate at which that magnetic flux changes. So what I want to do now is see if we can't use this idea, right, of Faraday's law of electromagnetic induction, Lenz's law, all of this stuff coming together, to see if we can't turn this a little bit on its head and cause motion to happen. I'll demonstrate this in sort of a practical way here in a second, but I want to lay out kind of a what if, and oops. Let's say that we've got like a couple of parallel wires. Think of it maybe like train tracks or something, okay? And on this parallel set of conductors, we put another like conducting bar that can slide along the track. So it's making a complete connection between the tracks. And we can pull it one way, we can push it the other, right? What we're going to do is we're going to close off one end of the track. We'll leave one end open, but we're going to make sure that we connect. And by doing that, what we have developed here, what we've made, okay, is a loop of wire, right? All the way around, there's electrical connection there. And if we grab this bar and move it, okay, we can change the area of our loop, right? If I push it to the left, the area is going to get smaller. If I push it to the right, the area gets bigger. I started off talking about magnetic flux as area being the one thing that's not very practical to change, right? It's mechanically a little bit harder to do. This is like the one example where we can actually mess with the area a little bit. Okay, let's drop a magnetic field in here. Whenever I get to pick the direction of the magnetic field, I tend to pick into the page because it ends up being a little bit clearer for me. If somebody says out of the page, I end up putting a bunch of dots down, and eventually the dots start looking like minuses, and it just all goes bad, right? So that's usually why I default to X's. Doesn't matter which way it's going. Okay, so we're going to grab this bar, okay, and we're gonna pull on it. Okay, we're going to start moving it to the right. Okay, and we're going to ask ourselves, all right, what sort of voltage are we going to get? Right, there's going to be number of turns, which in this case is just 1, right, times the change in magnetic flux divided by time. So I've got to go in like yesterday's lab, and I've got to figure out, right, of everything that's here, right, what's the thing that's changing, right? Where's the delta, right? Is it magnetic field, is it area, or is it angle? Well, I already told you it's area, right? We're going to be increasing the area of this thing as we drag the bar along. So I gotta figure out a way, right, to kind of figure out what this change in area is. And the area of a rectangle, let's call, I don't know, let's call the horizontal dimension, like this, whatever distance this is, we'll just call it X. And let's just call, for lack of a better thing, we'll just call it L. No, we don't want to do X and Y. So basically the width of the track is L, the distance from track to track is L, and then we have this, like, how far are we from the closed end, right? So that lets me write down this change in area. Okay, so what's the area of a rectangle? Length times width, right? So that's, in this case, it's going to be X times L. But is L changing or staying constant as we pull this bar? It stays constant, right? So really all we have, the delta gets assigned to delta X, right? Because that's the thing that changes, and the L stays constant. So now I've got to kind of put this all together, right? So I'll have an EMF. It's equal, and you'll notice I dropped my minus sign because I'm not doing Lenz's law right now. And I'm gonna just put in 1 for n so I can stop worrying about that. So what have I got? I've got a B delta X times L, right? That's the area. And then what's the angle here? between the area of the loop and the magnetic field? Which way does the area of this loop point? What are the two ways it could point? Remember, the area vector is perpendicular to the actual area itself. So the area vector of this table points up or down. So which way does the area vector of this loop point? Like either in or out, right? That's the only way to be perpendicular to the surface, right? Okay, so the angle between something pointing in and something pointing in is 0. And what's cosine of 0? 1. Okay, so we don't have to worry about that. So we have b times the change in horizontal distance times L. So that's b times area. The cosine theta is 1. The number of turns is 1. And then I divide by delta t. All right. What's delta x over delta t? Think physics 2a. What's a change in distance over a change in time? It's velocity, isn't it? Okay. So we can write this voltage, this EMF that's produced, okay, as b times, we usually write BLV. Okay, do it in alphabetical order. That voltage right there is called motional EMF, not to be confused with emotional EMF, which is what you experience when you're trying to do Lenz's law. Motional EMF is a voltage that is produced when a conductor moves through a magnetic field. In this case, our conducting bar is sitting on a pair of tracks, which allows the circuit to be completed, and the voltage will cause a current to flow. And if we were careful and we pulled on that and we pulled on it fast enough and we hooked, say, I don't know, a light bulb up to the track, we could actually light the light bulb by moving the bar, right? The motion of the bar, its velocity, right, times its length, times the magnetic field that's there will give us the EMF. And if we know, say, the resistance of the wire or the light bulb, we can find the current, blah, blah, blah. However, motional EMF can happen without an actual closed circuit. So we don't have to close one end of this track. We can still cause voltage to happen across the bar by simply moving it in the magnetic field. And this is what happens to any conductor that moves in any magnetic field. Can you think of any situations, everyday life, where a conductor is moving through a magnetic field? Street lights. Oh yeah, we didn't talk about street lights. Remind me about that one in a second.
So I have a light switch in my room.
Okay.
You can slide the switch to change how bright the light.
Oh, the dimmer, that's different. That's just changing the resistance.
I thought it
Yeah. No. Anytime when a conductor moves through a magnetic field, like through a constant magnetic field. You guys got to think bigger. You just did it this morning to get here. Your car. What's your car? It's a conductor, right? It's a cage of metal, right? And it moved through a magnetic field. The Earth's magnetic field, right? And so a voltage gets produced as it's motional, the motion of the car moving through a magnetic field. Your car doesn't sit on a track, so we can't complete a circuit, but there is a potential difference that begins to develop across your car as it moves through the magnetic field. Now, if you're stopped at a stop sign or a stoplight, is there any EMF being produced from that? No, because you're not moving, right? The velocity is 0. You do need the conductor's length to be perpendicular to the field in some way, shape, or form, okay? If you take a straight wire and you send it along the same direction as the magnetic field, it doesn't do anything. All right, so a more extreme case of this would be an airplane. And what I'm going to do now is I'm going to attempt to draw an airplane. This is a top-down view. Maybe. Eh? Eh? So it's going to be moving this way, okay? And it'll be in the northern hemisphere somewhere, so the magnetic field will be pointed in everywhere. So we've got it moving, right? The plane has a wingspan. We'll call that the length of the conductor, okay? And it's moving at speed v. So at cruising altitude, planes usually move around, like when they're up at high, like 30,000 feet, they're going about 900 kilometers per hour. That's about 540 miles per hour. And so we can go ahead and calculate, again, if we knew the wingspan of this plane, which for some reason I did not write down, we could calculate. So we need to know the Earth's magnetic field, which is usually about half a Gauss, so 0.0005 Tesla. And then we'd have to know the wingspan of the plane. Usually that's like 30-ish meters or so. And then we could put it all together. I went and calculated it apparently, but didn't write down any of my initial numbers, okay? They want to guess what the voltage across the airplane's wings is while it's in flight? Big number, small number? We're all going to die. I'll never get on a plane again now that Mr. Balogh told me that there's a voltage. Turns out to be half a volt. It's pretty small, right? So you need really strong, the Earth's magnetic field is pretty weak, okay? So you need strong magnetic fields in order to have any sort of like major contribution to this. As soon as the plane touches down and stops moving, the voltage goes away, so there's no danger. They don't even really need to design around this feature because of the shielding effect that the aluminum frame of the airplane has for the electronics inside. I wanted to just kind of give that calculation to show you that you really need either a lot of field, a lot of current, right, in order for this to be a thing. But let's reverse the idea, right? So instead of us grabbing the bar, right, and pulling it to change the area, what if instead we attempted to suddenly change, say, the magnetic field that this contraption is sitting in? Well, I've got that right here. This thing right here, okay? There's an iron core bar. This just helps to make the magnetic field stronger, okay? And that this iron core bar is going to be put inside of a coil of wire right here, okay? So I've got a bunch of loops. I've got a solenoid of wire here, right? Okay? And this is connected, okay, to the AC current, right, coming out of the wall. And I've got a switch on here, okay? And I'm going to take this aluminum cylinder here, okay? I'm going to thread it over the device, okay? So with no current flowing in here, what's my magnetic field? 0. From the solenoid, there's no magnetic field coming from the solenoid. We're going to generate magnetic field in this solenoid. As soon as I hit the switch, we're going to go from no magnetic field to a lot of magnetic field because we're just hooked up to 120 volts at probably draw about 8 amps or so, okay? So this aluminum cylinder will experience suddenly, right, a change in magnetic flux. And according to Lenz's law, what is it going to say? It's going to say, right? I don't want that, okay? And it's going to generate a field that's opposite, okay? Well, the stuff coming from the wall is alternating current, meaning that instead of just going in one direction all the time, it switches direction, okay, 60 times a second. Actually, it runs at 60 hertz. We'll talk about this in a few minutes, right? So it switches direction about 120 times a second. So that means that this ring will go from nothing to something, and then 1/120th of a second later, it's going to switch the direction. And then 1/120th of a second later, it's going to switch it again. And then switch it again. And then, right? Okay, back and forth like that. And so this ring is going to be like constantly going, right? Over and over and over again. You won't sue me, right? Here we go. Right? That's pretty significant launch, wasn't it? Okay, it wasn't just a small thing, right? It's like I can almost get it to hit the ceiling, right? Okay, so we caused motion because we simply changed a magnetic field very rapidly, right? So the voltage, the current, everything that was being generated here caused that motion to happen. All right, video game fans, what is this? Halo. You guys probably don't play Halo, it's too old. Any weapon in a video game that uses electromagnetism to shoot. Railgun. We took a projectile, a physical projectile, and instead of using gunpowder, right, chemical reactions to propel it, we used electromagnetism. So basically what this is a railgun, right? All right, so this is the same size, right? Same height, everything. It's just this one's made of brass, and brass is heavier than aluminum, okay? So what's your prediction for how high it goes? Not as high, right? Because it's heavier. And sure enough, right, it didn't go as high, right? It's the same amount of force because we've got the same like number of turns, we've got the same area, we've got the same changing magnetic field. It's just this has more mass, right? And so it's harder to like get it to accelerate. All right, this one is half the height, but made out of the same material. These are both aluminum. It's just half the height of the other one, okay? So full height, almost touch the ceiling. What's your prediction for the half height one? We're going to hit the ceiling or not go as high? Through or half? I don't see any holes in the ceiling yet. I've been working on it. We ready? Why didn't it go as high? The what? The number of turns is smaller, right? If this is 1,000 turns, then this one would only be 500 because it's only half, right? Now, technically, there aren't any like loops of wire in here, right? It's all solid metal. But effectively, the more material, even though it was more massive, right? We got greater benefit from the increased N, right? And so it experienced more. No, that has more to do with rifling and aerodynamics. Because bullets use gunpowder. Okay, so I've got the same, right, sort of thing here. Ready? Can you see it? Yeah, there's a slit in this one. Okay, this isn't a complete loop. So why didn't it go anywhere? It's not a closed loop, right? Okay, you need the closed loop in order for there to be any, it can't be any circulation, no Lenz's law, none of that kind of stuff, okay? So that's motional EMF. I will demonstrate right here, and then we will get to stoplights, okay? This right here is a light bulb, okay, that has been connected to a coil of wire, right? And so it's just literally straight from this coil directed into this very tiny light bulb here, right? What this will let me do is it'll let me hold it right here, okay, around the core of this device, right? But I want you to notice there is no like physical wires connecting the solenoid here to the coil of wire that's connected to the light bulb. But we can light the lights wirelessly. How does your phone charge wirelessly? Just like that, okay? Inside of modern phones, okay? Here, I took the back off my little wallet thing here, right? Do you see that ring of magnets right there? Okay? There's a similar ring of magnets on the back of your phone. That's how the phone like snaps onto its charger or whatever, okay? But near that ring of magnets is a coil of wire. That coil of wire is talking to another coil in the charging pad. the one in the pad switches its current back and forth, it'll communicate that to the next coil via Faraday's law of electromagnetic induction, and you'll have your phone being charged by induction. Those are inductive chargers. This was an inductive thing. Now, people are like, well, why don't we do wireless power and just send it everywhere? Okay. The problem is with wireless like energy transfer is to do it right and to do it with enough power to light bulbs and run microwaves and do all that kind of fun stuff. It basically means we need to broadcast at a frequency that would shut down like most pacemakers, okay? And like cook birds in mid-flight and all that kind of stuff. So we generally try to avoid causing medical harm to things. So that's why we don't do like wireless power transmission. It can really like wreak havoc with other electrical systems. Wires work pretty well for most things, and when it comes to phones and toothbrushes and that sort of thing, then you can have a little inductive charger. It's not going to get in the way. It's not going to be doing it at a frequency that's going to shut off medical implants. All right, stoplights are mentioned, right? This isn't so much motional EMF as it gets back to this concept and idea of Faraday's law of electromagnetic induction being used as a sensor, right? Have you ever, so you have like the road, right? And then you have the traffic light bar sits over the thing, right? It's like a top-down view, right? And the cars are all coming along. And then you'll see a circle cut out of the street a little bit, right? Or like they cut it and then they put tar back in it or something like that, right? And then sometimes you'll see some lines that are coming, like, and then there'll be another set like that's further down and they'll kind of run the lines like that. Those are coils. They put a big coil in the asphalt and run a cable to it, okay? As your car moves over that big coil, the coil can sense the presence of the metal of the car. The coil actually has a very weak current that's flipping around in it. And as soon as any metal gets close to it, it affects the magnetic field in that coil. And Faraday's law of electromagnetic induction starts to cause changes, and Lenz's law says, no, I don't want to change. And the computer that's sitting there listening to this, right, will sense that there's been a change. And so it assumes that a big piece of metal just went over, and big piece of metal equals car, and car equals I should turn the light red for a long period of time. It's supposed to be the other way around, right? It's supposed to be like sense that the car's there, turn green. I always feel like though the civil engineers are just mean and they program it so that when my car is showing up, right? I do have former students that work in the Department of Traffic here in Fresno County, right? So I'm sure that they just turn the license plate detectors. Okay, Mr. Balogh's license plate number, turn it, red, right? The instant I turn around the corner, right? And the light will just turn red, right? Sees me coming. It's supposed to be able to tell whether or not like traffic is there or waiting at the light, okay? There's other sensors, but that is a main one. You'll see them on the highways too. That's how like Google Maps knows what the traffic is. Among other things, right? They can get data from the Caltrans network about like how many cars are going over per time, how fast the cars are moving over the sensors. Google then aggregates that with other people that have turned on the ability to share the information about where they are at all times and that sort of stuff. And you get this picture of traffic patterns and all kinds of stuff that's going on. So all of that being brought to you by Faraday's law of electromagnetic induction. Let's do a quiz. Ramifications of Lenz's law. So I'm going to play a video here. And this video is going to introduce to you, it's not a new electric field, but there's been an electric field that's been hiding in plain sight the whole time. That was supposed to be a delta. And it's the electric field that's been hiding in plain sight the entire time is there in the EMF. So that voltage, that EMF that's being produced in Faraday's law of electromagnetic induction is a circular voltage. It's going around a loop of some kind. It could be a square loop, it could be a circular loop. I don't care what shape it is, but a circuit is being completed. And in order for that circulation to happen, the electric field that is associated with that voltage has to be circular also. So this is just a new shape for a field that we've always up to this point assumed was nice and straight, like started on positive charge, ended on negative charge. Well, here's a new one. Same electric field, it's just going to look like a magnetic field. Of course it lost it. It always loses it. There we go.
But when the magnetic flux through a loop changes with time, it creates an electromotive force around the loop.
So there's the EMF. Don't worry about the integrals.
And that electromotive force is due to an electric field whose line integral is not equal to zero.
Meaning it circulates. Yeah, don't worry about the integrals.
There is a way to make electric fields circulate after all. And it's accomplished by changing the magnetic flux. When Faraday discovered that a changing magnetic flux could make an electric field circulate, he added something extraordinary to the laws of electricity and magnetism.
The extraordinary thing that he added, right, was a symmetry that exists between electric and magnetic fields. Prior to this, the idea that electric fields started on positive, ended on negative, and that magnetic fields form these closed loops, right, was kind of like that was a difference, one way to really tell the difference between these fields. And what Faraday understood in thinking about induction was this concept and idea that no, you're going to start circulating electric field. So electric field can look like a magnetic field if the electric field that's being produced is from Faraday's law of electromagnetic induction. And so we open the door, okay, on a type of symmetry where electric fields can look like magnetic fields. Now, it would be really awesome if we could sort of get the other symmetry in place, right? That like a magnetic field would look like an electric field that starts and stops on charges. Still haven't found that one yet. We're working on it, but there's a different symmetry we're going to exploit when we start finally getting into optics, where we will, I don't want to, spoiler alert, I don't want to spoil it too much for you. But this concept and idea of electric fields, right, being induced right here means that these electric fields, right, can't see. Of course not, because I forgot to hit the button. Thank you. These electric fields that are being produced, right, are circulating. That voltage there on the side, right, you can't have voltage without having electric field there, right? There's a change in voltage, there's going to be electric field, and that electric field, right, it's electric fields, it's circulating, the electric field vectors are tangent at every point on the circle, just like the magnetic fields are. But we're building up a picture about how these electric and magnetic fields interact with each other, okay? So that leads to this concept and idea called an eddy current. This is an eddy as in an eddy in a river or a stream. What's an eddy in a river or stream? What does that look like? Have you ever been rafting? Water flowing down the river tends to go kind of in one direction, but every once in a while you'll see like a little miniature whirlpool form. It'll be this circulation, okay, of water. Maybe there's a rock under the surface, right, that you can't see, and the water's kind of being forced to go a different way, and you'll get these things called eddies, okay? They're just very minor circulations, and that circulation might just flow with the rest of the river, right? Okay, but you'll get these twisting patterns within the main flow. So an eddy current is a current that is circulating within a conductor of some kind. And we can exploit these eddy currents. We did it with the magnetic brake that I had last time, okay? It was forming eddy currents. It was forming circulations of currents within the paddles of that pendulum. But I have brought with me a demonstration that can show the power of eddy currents. And of all the demonstrations that I do in all of my classes, this is by far the most dangerous one that I ever do. This one, I've told my wife, if I die at work, it was this demonstration that did it, okay? Because what we have in here, and it's not plugged in yet, so I'll show you, okay? What we have in here, okay, is two very large capacitors. These are oil-filled capacitors, and I can store enough energy in these capacitors to kill me like 15 times over, right? So we're gonna charge these up to about 9,000 volts at a certain capacitance. It's just gonna be an enormous amount of charge in here. And then the circuitry behind here is responsible for somewhat safely delivering all of that electrical charge through this coil up here, okay? This coil, right, is going to go from having no current in it whatsoever and therefore no magnetic field to having, well, in scientific terms, a butt ton of current, okay? It is like the amount of current is going to be in the hundreds of amps going through this coil, okay? What I'm going to do is I am going to, in this coil, let's see, can I bend it this way? Yeah. I am going to put an aluminum can. Dr. Pepper or 7-Up? Dr. Pepper. We're going to do both, so it doesn't matter. All right, so I'm going to put this aluminum can in the coil like that, okay? What I want to do right now, while I'm working on kind of getting this set up and getting it into a safe mode and hopefully not killing myself, I'm going to play a video, okay, that is going to try to explain what's going on here, okay? Their equipment setup is slightly different than mine, but close enough, and you'll be able. They're going to show you an animation or a graphic, right, that will explain what's going on. It's going to be lots of things going on, but essentially, one coil is going to make a whole lot of magnetic field, and the aluminum can is going to respond with an eddy current and Lenz's law and Faraday's law of electromagnetic induction. And what does Lenz's law say? No.
This demonstration uses an electromagnetic field to break a cola can into two pieces. An empty aluminum cola can is inserted into this three-tube coil. This 400 microfarad capacitor will be charged to 3,000 volts as when that is mirrored, and then will be discharged through the coil. Let's charge the capacitor. When the capacitor is discharged, it creates an electron current in the coil, which increases rapidly to a large value. As the current increases, it produces a magnetic field, which also increases rapidly with time. A rapidly increasing magnetic field induces an electric field circling the axis of the coil. This electric field produces a large electron current in the aluminum can. The electrons circulating around the can in the magnetic field experience a magnetic force directed primarily radially inward, but with a smaller force directed outward along the axis of the can. The capacitor is
Okay. So a lot of stuff going on there, right? But we've got like magnetic fields generating currents, which make magnetic fields of their own. We know there's going to be opposition here. And the video did say what was going to happen to the can, right? Okay. So I call this my electromagnetic can crusher, right? because, what's that? Yeah, go ahead. You're going to film my death? Right? If I die, class dismissed, and if somebody wouldn't mind telling the police, that'd be good. All right. So I really have to concentrate while I'm doing this because, again, I don't want to die. So I'm going to be shouting out the voltages as they go up, okay? So like 1,000, 2,000, 3,000. And part of this, I see your hand, one second. Part of this demonstration is it could go off prematurely, right? There's a case where if I haven't gotten it tuned just right, it could, like at 7,000 or 8,000 volts before I get to 9,000 volts, it could go off, okay? So I apologize if it goes off prematurely. We'll all be surprised. It's going to be a really loud noise, okay? When I trigger it, it will be a loud noise, so you might want to cover your ears. The other thing is, you guys kind of need to watch out a little bit. I'm pretty sure I haven't aimed it at you. Yes?
Okay, so let's say worst case scenario, you're on the floor and something happens. Is CPR gonna help or no?
It'll keep me alive until the people get here with the AFib. Yeah. Okay, all right. Spoken like a true nurse. All right. So I can't really hear you. I've got all this on, so if they're screaming, I won't know about it. This is the only demonstration that has a key. And the other physics professors asked me to come in and do it. That's how scared they are of it. All right. I think we're ready. Plug it in. Get all my settings right. Correct. All right. So system is on, and I'm going to begin charging it now. All right. Seems to be working. So there's 1,000 volts, 2,000 volts, 3,000 volts, 4,000, 5, 6, 7, 8. There's 9. Okay, you ready? 3, 2, 1. Oh, God. All right. System is safe. Where'd it go?
A piece of shrapnel fell.
Yeah. Okay. All right. So here's one half, and there's probably pieces of shrapnel. Where's the other? Over here. Okay. Right. Okay. So you can see what Faraday's law did, right? We literally crushed. It's called theta pinches, squeezing like that. And in the video, they said there's a smaller component along the axis of the can. It still shot out at about 30 miles an hour, okay? So I'm going to pass these around, right? Be very careful. These edges are like razor sharp, okay? I will not be held responsible for anything you do to yourself, okay? If I pass these around, okay? So
Is it hot?
it's a little bit warm, yeah. Okay, we'll start this one back here. And they'll kind of meet in the middle, okay? But you can see, pass those along.
I'm worried right now. Is it off?
It's safe, it's not off.
Can you turn it off?
No, because I'm going to do it again. All right, so yeah, there's a big wand that I use. Like, there's situations where it may not go off when we trigger it, and so now you have essentially a bomb. And you have to, not that it's going to like explode outwards or anything, but you've got enough energy in here to like do some serious problems. And so you have to be able to take all 10,000 volts that this thing's capable of and discharge it slowly. you see this big, huge green thing that's in here? This is a huge resistor. And so when I've had to actually discharge this thing from its full, it like pulls like an arc, like a plasma arc off of it while you do it. It's pretty intense. This is definitely something you want to use the one-handed rule on. Very definitely. Okay. So here goes 7-Up. The manufacturer, it makes absolutely no difference. Can you smell the burnt sugar? All right. Let's see if we can do this again. This is as exciting as it gets, ladies and gentlemen. It's all downhill from here. Check everything. Oh, I got to check something else. This thing has a tendency to blow itself apart. Yep. Yeah, okay, so there it blew itself apart. So I've got to fix it real quick. It's not hard. I do need to fix it. Okay, so what I'm doing here is it's like totally safe and inert, like it can't do anything. Its safety is on. It's got 2 safeties on, actually. And now I've got to get in here and I've got to fix this part. It blows the wires out of their connectors. It's so violent. And there's like a lot of black soot around it. It's pretty fun. Okay, that one's good. That one's good. That one's good. That one's good. All right. I believe we are ready. Safety off. Take the other safety off. All right. I think we're ready. I've actually never seen this thing work. I'm always on the ground pushing buttons. Plugged in. On. Last check. Charging. Here we go. There's 2,000. And 2,500, we passed the lethal limit, right? So it's now lethal. 5,000. 6. 7. 8. And there's 9. You ready? Here we go. 3, 2, 1. And safe. All right. So yeah, they feel kind of warm. Here, I'll start this one here, and we'll start this. Oh, you guys have got them here in the middle. Did everybody get to see them? Everybody got to see? Okay, we don't need to spend it. But is this one warm? Yeah, right? They're a little bit hot, right? After having done it. Can you feel the heat? Yeah, right? So, yeah, that's the smell of the sugar left over from the soda. There's a little coating on the inside of the cans that they use to kind of keep the stuff from corroding the inside of the cans. And then you're probably breathing in vaporized aluminum too. So all kinds of good stuff, right? Give me a second. I got to make sure this thing is totally safe. This is all my high voltage training coming in. Keeping me alive. All right, there we go. Totally safe. can't, totally inert, can't do anything anymore. Even if we plugged it in and pushed buttons, it would just short circuit. Not cause any problems. All right. It's hot in here. Thank you. I didn't die yet. Okay. No. I just, I'm willing to sacrifice a lot for your education. Is all. Let's see. This thing went to sleep. I think my iPad might have rebooted because of the pulse. There's an electromagnetic pulse that gets shot out. What are we on? Oh. That wasn't right. This is what I want to do. Ah! Okay. So eddy currents, the circulation of the electric field and current in a device. We watched that. Okay. All right. Let's finally get to some real practical applications besides spending inordinate amounts of electricity trying to cut cans in half. What's a transformer? It's more than meets the eye. A transformer it's not this. Just being clear, okay? Right? It's these, okay? And you've probably seen them in various spots, like in your neighborhood. Maybe your neighborhood doesn't have power lines. Maybe it has like a little green box, big green box somewhere on the street. You probably have seen a charging brick for like a laptop, okay, or other device that you plug into the wall. The ones on the poles are true transformers. The ones that we plug into the walls like these, it actually does two things. It changes AC to DC, which is not what a transformer does. A transformer trades current for voltage. And we'll explain why we need this here in a second and why we're talking about it in a chapter with Faraday's law. Rectifiers change AC to DC. Okay, and just about everything that we use, like computer-wise, phones, tablets, all that kind of stuff, they need direct current in order to function, the oscillating currents of AC. But direct current, this is a little bit of a lie, but it's a good one. Direct current isn't good at transmission. So sending direct currents long distance can be problematic. AC is much better at being transmitted from the place that it's generated to the place where it needs to be used. And so we have this issue where we've got to be able to not only switch between AC and DC, depending on the application, but we need to be able to do so efficiently. And this is where these transformers come in. Okay? So what's going on here? A transformer is the physical manifestation of Faraday's law in your daily life. It consists, this is not what they actually look like on the inside, but they consist of a central core, a common bar around which two different coils are wound. You send AC into the side called the primary coil, and whatever flux, magnetic flux is in the primary coil is matched, because they share the same core, by the secondary. Now, if the number of turns is identical, if they're both, say, 1,000 turns, then you will get exactly the same voltage that was sent into the primary in the secondary. But the neat thing is, because the flux stays constant, if we change the number of turns, like we put the secondary and we give it more turns or less turns, we can actually change the amount of voltage that the transformer puts out. So your house, when you plug into the wall sockets, right, that comes out at about 120 volts. What does your charger for your phone need? USB standard? 5 volts. That's it, 5 volts. Now the different wattage, right? 20 watt, 40 watt, 100 watt, that changes based on the amount of current that's being drawn. okay? But the voltage is 5 volts, okay, for USB-C, USB-A. All the USB standard is a 5-volt standard. And so we need to be able to go from 120 volts alternating current to 5 volts direct current. The rectifier takes care of changing it. We really can't talk about that until we get to quantum mechanics. But as far as the transformer is concerned, this is directly related to Faraday's law of electromagnetic induction. So what have we got going on here? We've got a primary side and a secondary side. And in the primary, I'm going to kind of draw this a little bit. Well, here, I'll do it like this. The EMF in the primary is equal to the number of turns in the primary times the change in magnetic flux through the primary. Transformers require AC current. You cannot do transformers with DC because you need a change in flux. DC will cause magnetic field to go in one direction and just keep going that direction and never change. So what we need is changing magnetic flux. We need the flip-flop that comes from AC current. In the secondary, I'm going to draw this one a little bit backwards, okay? I'm going to say change in magnetic flux over time times N2 equals voltage in the secondary, okay? Remember I said that the flux is the same. Because they're both wrapped around the same core, whatever flux is in the primary will be the flux that's in the secondary. So we can set the flux equal to each other. If we divide both sides by the number of turns, and we put this all together, what we find out is the voltage in the primary divided by the number of turns in the primary is equal to voltage in the secondary divided by number of turns in the secondary. Your book, yeah, okay. So that's what I would get out of it. But your book slightly alters this to say voltage. Do they do secondary first? Okay, this is what your book writes down. Voltage in secondary divided by voltage in primary equals number of turns in the secondary over number of turns in the primary. I actually don't like that one. This is your book. Okay. I find this one in the red box to be a little bit more, but you can decide. You can decide what you want to do, right? They both say exactly the same thing. They're just rearranging like what they're putting in the denominators and all that kind of stuff, okay? I often will just solve this one so that the voltage in the secondary is just equal to N2 over N1 times the voltage in the primary. So pick your poison. Those 3 boxes are saying all exactly the same thing. The relationships are exactly the same. It's just a question of where you want to put stuff. So let's say, just for sake of argument, that the number of turns in the secondary is bigger than the number of turns in the primary. I don't know. Let's say primary's got 100 and the secondary's got 1,000 turns, right? What will the voltage in the secondary be compared to the voltage in the primary? If N2 is bigger than N1, what happens to this fraction? Like, is it a number bigger or smaller than 1? It's bigger, right? So that means that V2 will be bigger than V1. Okay? And if the factor is a factor of 10, like my example, 100 versus 1,000, right? Okay. Then, if the input's 5 volts, then the output would be 50 volts, right? Okay. It's whatever the ratio of turns turns out to be the ratio for the voltages. Okay. So when the number of turns in the secondary is bigger than the number of turns in the primary, we call this a step-up transformer, because the voltage will increase on the secondary side, okay? You want to take a guess as to what happens if the number of turns in the secondary is less? That's called step down, okay? And that's what's happening in your neighborhood, right? With the transformers that are on the power poles, they're taking about, in the neighborhood it varies, but roughly around 20,000, 15,000 volts on the power lines, and they're stepping it down to 240 volts as it runs into your house. and then the 240 volt line gets split at the panel to become 120. So they're stepping down the voltage again because it's more efficient to transmit at high voltage than it is, but high voltage isn't very good for doing like everyday tasks in the house. You don't want your electric stove running at 15,000 volts, okay? That would just be a meltdown, okay? So that's why transformers exist, be able to trade back and forth. You should be aware that no trade comes for free, okay? And there is a corollary to this, okay? Because energy is always conserved and the power delivered has to be consistent no matter what the voltage and current is. The current in the secondary will be equal to the number of turns in the primary divided by the number of turns in the secondary times the current in the primary. So what happens with current is it gets reversed. So step up and step down refer to the voltage. But if you increase the voltage in a transformer, you decrease the current. So you're trading voltage for current, but you're keeping the power the same. The actual amount of electrical energy per time that's flowing in the circuit stays exactly the same. Energy must be conserved. However, we trade voltage for current. So in a step-down transformer, if the power lines are going from 20,000 volts to 240 at your house, what's happening to the current? It's going up, okay? And so we trade voltage for current all through our electrical system, okay? The calculations are not hard. They just aren't, okay? 800 turns in the primary, right? So the primary is 800. Secondary is 200, right? What's the output voltage? Well, they're asking me for the voltage in the secondary. Well, that was the number of turns in the secondary divided by the number of turns in the primary times the voltage in the primary. Well, N2 was 200, 800 in the primary, right? What kind of transformer is this? Yeah, this is a step down, right? And it's stepping down by 1/4, isn't it? 200 over 800 is 1/4. And what's 1/4 of 120? 30 volts. Okay? The current, which originally was at 5 amps, right? In the primary, right? Since it stepped down 4 times, what happens to the current? It steps up 4 times, right? So the new current is going to be 4 times the original current, or 20 amps. Okay? So again, calculations aren't that hard. However, you just need to be organized, right, with your number of turns and all that kind of stuff. In the last little bit here, I've only got like a couple minutes. I do want to do demonstrations so that I don't have to bring them next week, and then I'm more or less finished with this chapter, okay? But what I've got here is an electrical motor, okay? In order to get this thing to spin, we need a device called a commutator on it. We need to be able to change the magnetic field orientation every time this thing spins around. If red and red are the same magnetic field, we want them. So what happens when 2 like north poles are together? They'll repel each other, right? But what happens like if it's spinning around and it's trying to get closer? Well, these 2 will push each other apart and the motor won't spin, right? We need it to be able to like push and then pull this one in. And then as it comes around, we need this to flip so that it gets another pull in. And that's what this thing up here called a commutator does. You'll see these brushes up here. They brush against the commutator. The commutator allows these coils in the middle to change north and south pole constantly. So if I turn this on and I give it some current, right, I can get motion, right? It's a direct current motor, but we're getting the spinning, okay? And it's not getting like locked up in its turning because of that commutator that's in it, right? Now, there are AC motors that you don't need the commutator. They just use the current flipping back and forth to do that. But I can reverse that process. So that was taking current, right, and getting motion out of it. All of Faraday's law of electromagnetic induction. This one, I've got a crank attached to a coil down inside that you can't see, and it's near some very large permanent magnets, right? That coil that I'll be rotating is attached to the light bulb, and it should come as no surprise, right, that I can light the light bulb by turning the crank, okay? So what's this called? This is the generator, right? Now, it can be kind of hard to see. People here in front, can you see the very dim? What's it doing as I spin? Kind of flickering, isn't it? Okay, so the faster I spin it, the more sort of bright it stays, right? But light bulbs, now LEDs cheat because of quantum mechanics, but let's pretend they're regular light bulbs. Why don't we see them flicker? 120 times a second on the AC, isn't it? Okay, that's too fast for our eyeballs to see the frame rate of. However, if you've ever taken video with your cell phone and sometimes caught the flickering lights of LEDs and stuff like that, okay? What's happening there is the frame rate of your shutter in your camera is being able to pick up the frame timings of the electricity running through the wires that power the devices. Modern phones tend to try to take that out with software. It'll detect that the lights are flashing and it'll smooth them out so that it doesn't happen. But just wanted you to see generators and motors. All right, on Thursday, we will do chapter 23, and we're going to basically do it in one day. And it's going to be okay. It's going to be okay. I will see you then.